guys, let's solve some more leetcode today. Let's solve this problem, Coco eating bananas. Cool. So you're given an integer array piles at I is a number of bananas of the ith pile. And you're also given an integer h, which represents the number of hours you have to eat all the bananas. Okay, you may decide your banana per eating hour rate of k. Each hour you may choose a pile of bananas and eat k bananas from that pile. If the pile has less than k bananas, you may finish eating the pile. But you cannot eat from another pile in the same hour. Okay, so if the pile has less than k bananas, you may finish eating the pile, but you cannot finish eating from another pile. Okay, return the minimum integer such that you can eat all bananas within h hours. Okay, with an eating rate of 2, you can eat the bananas in 6 hours. With an eating rate of 1, you need 10 hours to eat the bananas, which exceeds 9. Thus, the minimum eating rate is 2. Okay, so in this case, if we go through here, right? If we go through this guy, and h equals 9 or something, right? Our output is 2. Now, why is our output 2? 2 is the minimum rate of which we can eat a banana. Okay, so in the case of 2, you would take 1 hour to eat this guy. It would take 2 hours to eat this guy, and then 2 hours to eat this guy, and 1 hour to eat this guy. So it would be 2 plus 2 plus 1 plus 1. So it should be 6. Then for 1, it would take quite a while to eat them all. So, okay, I see. This is quite a cool question. I don't immediately know how to solve this, but let's just work through it. Okay, let's look at another example. If we look at this guy, we notice that h equals 4, which means the limit equals we can only take 4 hours to eat this. Now, since we can only take 4 hours to eat this and there's 4 elements, we kind of need to take the maximum element in this case. But that's sort of weird, right? That's sort of a weird way of thinking it. I feel like in this case, well, I guess if we were just like not looking at time complexity and stuff like that at all, my first solution would just be to start from, I guess, like 1. I guess 1. We would start at 1, right? Because we know 1 is the worst amount. Oh, I guess like a clarifying question would be, do we always assume there's a solution? Like, what can h be as well? Like, can be h like negative or what? Do we always assume there's like a solution? For example, I know like 1 will not work. I guess you should go higher. You should go until you can find 1. So I guess for my idea would first be to start from 1, and then so you'd start with a rate of eating of 1. That'll be obviously the minimum. We want to find the minimum, right? So we would start at 1, which is the lowest that you can possibly go. So then 1 would just be, okay, you calculate how long it would take. In this case, you just like sum up everything. But okay, so basically to calculate the time, I think what you could do is take an element. If this is like piles at I, right? We could just like piles at I, and say like the element is divided by our rate, which for example we could just say our k equals our rate, right? It equals k, and we gotta like floor it, okay? Or actually no, we gotta seal it. So we're gonna round up always. So for example, if our k is equal to 2 and our pile is equal to 3, then it's gonna be 3 divided by 2 floored, which equals it's just gonna equal 2. Because you're actually gonna need to take 2 hours to eat it, because you're gonna eat 2 bananas and then you're gonna have 1 banana left over and you eat that. Okay, so that's my initial thought process behind this. I think it'd be very slow. Okay, so like worst case scenario, it goes all the way up to the max value, which we can call like the max value equal to like m or something like that, right? And n is the length, so it would be like it'll end up being like n times m, which is really not ideal. Is there like a better solution though? Okay, you should aim for a solution with o of n log m and O of n one space where n is input size and m is the maximum size of the array. Okay. So how would we do that? That looks a lot like binary search. It seems like we're iterating through the whole array and doing binary search on it. Huh. So how would you do that? That's a good question. Okay, how would we use binary search? How would we even use binary search in this case? Because it's not even sorted. It's a question. If we can't sort it, well, I guess if you pay attention to it, it doesn't really matter the order. For example, if this was like 1, 2, 3, 4, you'd still have the same. It would still take the same time to actually eat the bananas. For example, if k was equal to 2, then no, you'd eat this, and eat this, and you'd take 2 seconds to eat this, and you'd take 2 seconds to eat this as well. And it doesn't really matter. Each element is independent of each other. So I think we could definitely sort the array for free in this case, sort of like quote unquote for free, because if our goal is O of n log n, then I think O of n log n, which is the time for sorting, would be fine. Yeah, I guess only if n is m is less than n, then our O of n log n would be valid. But also, like, okay, I'll just assume we'll just sort it first. Okay, so after we sort the guy, how is it gonna help us that we're going through it like this? So okay, how many binary searches do we need to do? So if we're iterating through the array, okay. Because the thing is, we want to go end up changing our value to this is kind of tough, I'm not gonna lie. We'll look at a hint. Given h is always greater than or equal to. So wait, so h is always greater than or equal to the length of piles. Can you determine an upper bound for an answer? How much time does it take Coco to eat a banana of X pile with X bananas? So wait, oh wait, yeah, there's an upper bound. Okay, yeah, no, I should pay attention to this. So h is basically our limit, and h is always going to be greater than or equal to the length of piles. Now, what that means is you can always yeah, I guess if you have the max value, I think you'd always be fine. Yeah, if you had the max value to eat the bananas. Wait, so yeah, okay, wait, so h is greater than or equal to the list. So what that means is the time we take. Okay, let's get a blackboard up here. Okay, the time. Gee, well, I don't really know how to use that. But okay, so in this case, the time it takes for us to eat the bananas is always going to be greater than or equal to the list. So in other words, if our k is equal to the max value within our array, then in other words, every single pile is only going to take 1 second, and like we're always going to be having the solution. So if k ends up equaling the max value of our piles, then we're basically good. So what did it say? Given that h is always greater than or equal to this thing, can you determine an upper bound for the answer? How much time does it take for a Coco to eat a pile with X bananas? That's a great question. Yeah, so okay, so in this case it's 4. This case is 1. this case it's 2. So we have 4 here, right? And then we have 2. So okay, wait. I guess my thought would be we would initialize k just to the max value of the array, which is like 4 or something. For example, if we're just looking at this case, let's just make a new example. We look at just this case, okay? We look at just this guy and we can initially just say our k is just our max value of this array, which in this case would just be 4. And we know k equals 4 is a valid solution. So we already have a valid solution, but we want the minimum. So that's actually not a valid solution, so I was lying. How are we going to go about finding the minimum? My idea behind this is I think we're going to want to sort the array. And then we could actually apply binary search on it to sort of like get a new k and see if that works. And in the case that k works, so for example, if 2 works in this case, we're going to want to do another binary search between these 2 elements. And that would take us to here. And then we would test out 1 and say, oh, 1 does not work. Right. And 1 does not work, so what does that mean? Move this guy up here. Oh, they're equal, and then we're done the binary search. I think that'll work. Let's see if it works on this. I want to test and see if this works on this. So for example, here you have h equals 4, which is actually equal to the length here. So initially our k is initialized to the max value. So our k, which is our rate, it ends up taking the max, which equals 25, right? And we know 25 works. So since 25 works, what we can do is say so do this, right, and then 25 and 4 here. So we want to do a binary search, and then we go down to 10, see if 10 works. Unfortunately 10 doesn't work, obviously. So in the case that 10 doesn't work, then we test out 23, and I don't think 23 works either. And then we cross and then we're done. So I think that should be fine. We'll try implementing that. So the idea is start with k equals max value of piles, and then we're gonna want to perform binary search for a new k value. Once we do that, then test. Do it until binary search is done. Actually, we're also going to want to sort the array beforehand. But yeah, okay, it doesn't really matter if it's like sorted or not. Okay. Okay, so if we want to just k equals what? K equals just the max between the piles. So how fast is this is the question. How fast does this find the max value? Why don't we just sort it and get the max, the last guy? That's probably faster. Okay, sorting array. Let's go sort an array. Okay, it's just called that sort. Okay. Okay. So let's get rid of these guys because this is. So okay, so we just call piles.sort, and this should sort the guy. Yeah, that's good. And then we're gonna say k is gonna be equal to piles at the length of piles minus 1. So that's like we're just gonna get the last element from that, and then we're gonna perform binary search on the piles until basically they cross. So L and R equals 0 and length of piles minus 1 respectively, right? Then we just say while R is greater than while R is greater than R is greater than or equal to sure. R is greater than or equal to L. We're gonna want to just do like a midpoint, which is equal to something, right? So the midpoint is going to be equal to L plus R minus L divided by 2. Okay, so this is basically, it's basically R plus L divided by 2, but just like getting rid of any integer overflow, but I don't think that would ever happen here. Yeah, so whatever. Okay, so we should like sort of check if it's good or not, right? So how are you gonna check if it's good or not? This is log m, but we're still gonna have to go through the array and check if it's good, verify if it's good. Okay, so I'm gonna define a new function. Define verify good is good. Right, self. I don't think we need self. It's gonna be more. I don't know, like bananas. And then what? 8. Oh, okay, well, we already have h. We actually can already access piles from here as well. So I think the only thing we need to pass in is the value that we're using, or like the k value. So pass in that, and then all we gotta do is just say just a counter, right? Counter equals 0 for now, and then we're just gonna go through piles, right? For each of the i's and piles, we're just gonna say counter equals counter plus the ceiling. What's the ceiling in Python? Seal. Okay, just seal. Seal of what? It's gonna just be the ceiling of. It's gonna be the ceiling of the I value here divided by k value, our k value. Yeah, so for example, if we're eating like 3 bananas and we eat at a rate of 2, that's gonna take us 2 hours, and this will do that. Okay, so, and then we gotta scroll our return if our counter is greater than or equal to, is less than or equal to the h value, right? And in the case that this is true, then we should return true. So that returns true, so that's good. So okay, yeah, we can just check that. Verify is good. That's a good function. Okay, so verdict, right? Verdict equals this guy. Verify is good with the value of m. So what is the value of m? This is piles of m, like this. So okay, so if our verdict comes out to be true, then what? So the idea is we're gonna see if we can go any lower. So we're gonna want to say r equals 1 plus hold on, r equals m minus 1, right? Because we know, we know the one we're going on is good. And also in this case, we're gonna want to update our k value, which k equals what? K equals piles at m. Yeah, I think this will actually work because like I was just thinking, like, if we have like a value that's like in between it, and you think that would work. I'm not sure if it would. Do you think it would work? I mean, do you think okay, if we had like h equals 5 in this case, what would work? We would need like 1 extra. I think only 23 would work in this case. 23 covers 1 extra. Yeah, I'm not too sure. We'll see. There might be a problem with my solution. Else if I don't know if it's elif or not. Well, I think it's just else in this case because then left will end up equaling. Okay, so in this case our verdict is not true, which means the middle does not work. So we're gonna want to say let's get 1 plus m like this. I think that should be good. And we don't want to update in this case because we don't know it's not working. So return k in this case. Let's go fix some errors. This is invalid syntax. Okay. Why is this invalid syntax? I don't know. What? How's invalid syntax? I'm doing too much Python, man. Counter. Okay. If counter is greater than or equal to h, then return true. Return false. Otherwise. What? Oh. Let's jump here. Okay, let's see. Yeah, this should be integer then. Ceiling. There's a problem with ceiling. Ceiling is not defined. Import math. Okay. Wait, what? Oh. Math dot. Ceiling. Oh, accepted. Let's see if it works. Okay, I got the wrong answer. Okay. So let's see what's wrong. Last executed test case. You see this guy, right? Output was 6. Expected. Okay, yeah. So exactly what happened between what I was thinking. So how would we do this? What we could do is like we could generate like sort of like a list from all the way from 0 to 1. No, 0 all the way to the max value. And then binary search through that. And then compare if it's good or not. But no. That's also, like, I'm hesitant to do that because they also said the space complexity is O of 1. So I'm not sure if you could probably do that like without doing an array or anything like that. That's a good question. Okay. Yeah, I'm stumped. Okay, in this case, our verdict is this guy, and there is at piles at m, right? Piles at m. That's not good. That's really not good. What's the best way to find a max value? I think the way you're finding is pretty good. But h equals 8, h equals 8, and 4 works in this case because 4 is good. Okay, I think we should just like generate an array and binary search that. But I feel like we could probably binary search without an array in this case, which is kind of goofy, but I think it would work. Okay, so if we're gonna binary search, what are we gonna do? So basically, we're gonna have a max value, right? Our max value in this case is 11 for this specific scenario, right? We want to get the 4. How are we getting to the 4? So okay, so we know 11 works, and we're gonna go through we're gonna divide by 2 in this guy. You know why we're gonna divide by 2? Because we're dividing by 2 because of a binary search. Because we're gonna divide by 2 and see, 5 works. Okay, so 5 works, then we're gonna move our right pointer sort of to 5 and our left pointer to is still at 0. So we're gonna go to 2.5. Okay, 2.5. 5 divided by 2 equals 2.5. Which goes to 2. And 2 is like, 2 does not seem to work. So we move our left pointer up to 2. And then we could say, 5 plus 7. Divided by 2 equals about like 4, 3.5. Which gives us 3, and 3 does not work, so when we go down here again, and we say, it's 3 to what? 3 to 5, so it's 8. 8 divided by 2 equals 4, so 4 works. So we need to change our way we're doing binary search, to be honest. But the way we're doing binary search is not really right. Yeah. Okay. Yeah, so I think this will still work. I think so. But it's just this thing not really work. Okay, so M in this case, yes. It should be M in this case. And then in this case it should be this. No, it should still be int, I think. Because we're still looking at ints. And left is still 0, but this guy's gonna be the max value, which is just k for now. Right? And this guy's gonna be this. And this guy's gonna be reset all the way to M. And we're gonna verify if it's good or not. And I think this should be good. I don't know, let's see. Division by 0, that's not good. Huh. K-val, so we're checking. Okay. Cool, if it's 0, you should return, bro. If this is kind of a weird edge case. Well, obviously it's gonna be false because you can't really do that. Accept it. Wow, good job. Well, see you guys tomorrow.